Thank you.
Thank you. Thank you, Madam Vice President. Thank you, dear hosts. Thank you, guests, friends, I should say. And thank you, interpreters. They will make this day, for me at least, very useful. And that's also something that I always like to recognize. My name is Olaf Kolkman. I'm the Chief Internet Technology Officer at the Internet Society. I've recently joined about half a year ago. And I want to say a few words about the Internet and maybe get to some developments. We'll see how long we have, how much time I'll have to take, and where we end. We'll take it free flow, so to speak. Oh, you're running. Oh, so that's okay. Internet, different players at different layers. I'm going to explain a little bit about the Internet based on. I'm having an argument with the stick. Based on the. I've got this thing. Based on this picture here. This picture is a model, an architectural model of the Internet. Some of the technologists in the room might have heard of the OSI model of the different layers, physical layer, transport, session, etc., etc. You can collapse this down into a model of 3 layers, which in the Internet we usually call the hourglass model, where you have a network layer, an application layer, and a very small layer that divides that binds these 2 things. I'm going to explain you a little bit about this model and why it is important in thinking about the Internet and thinking about this model when you make policy decisions and do the things you do on the Internet. What is the value of this hourglass? So I made a division about application layer, network layer, and a middle IP layer. Now, IP is the Internet Protocol. That's the thing that Vint Cerf invented together with Bob Kahn and with Steve Crocker. And it's a protocol element. It's basically the packets that traverse the network. It's a layer that is being offered on which applications rely. Applications basically look down in the hourglass, and the only thing they see is IP packets. They don't see anything more. They don't see the physical infrastructure of the network. And at the application layer, that's where all the innovation happens. Or that's where the innovation happens that matters to us, users of the Internet. That is where people have invented things like Facebook, like Twitter, but also other types of applications that we use on the Internet. Email is one of these examples, but also telephony. Usually, we nowadays do basically all our telephony over Internet technology. And you can just freely sort of create new technologies over there in the application part of the hourglass. Just taking into account that the only thing you have to develop through is IP technology. You don't have to know about the inner networkings, the network functionality. Fun stuff, business, etc., etc. The term that we use for this way of freely application development is permissionless innovation. You don't have to ask the network for creating applications at the top. The only thing you have to do is, develop against the IP protocol layer. It's the network layer that offers this IP to the applications, completely independent. And it's made out of very many different networks. This is a very impressive picture. This picture is showing a snapshot of the Internet. Every node in this network, so not every line, but every node in the network is a single network. So every point here, every point is a single network, and all these networks operate autonomously. They make their own business decisions. They make their own decisions about technologies. They make their own decisions about how to charge. They make their own decisions who to neighbor with. And the only thing that they have to do in order to make the internet work is deliver IP so that the applications can use it. This innovation on this scale has driven down the price of bandwidth. This is a Western European view, early mid-2011. This is from a colleague from the Netherlands who gave me these numbers. An SMS text message cost per megabytes per second is $210 million if you calculate the cost of SMS messages per megabyte per second. Those are very expensive. If you look at the cost of a fiber cross connect in a data center, a megabit per second costs $1. And these are prices from 2011. They probably have dropped. And obviously, this depends on where you are in the world, this price tag. But the point is that because we had this network layer, and the only thing that people have to do is deliver IP, it became a very highly competitive market. And IP has turned into a commodity. The middle layer, the IP, the waste of the hourglass, as we normally say, that's where things are binded. And in order to bind applications to the network and make the network of networks an internet, we have to do a couple of things. And we have a number of properties. There's this loose coupling between the upside and the downside of the hourglass, which gives us functional interoperability. You know, if somebody develops an application here in the internet, Kyrgyzstan builds something new, that might be adopted at the other side of the world, just because there is functional interoperability. But adoption of technology in the internet is always voluntary. There is no central system. Remember that network that I showed you, that picture? It's completely meshed. You cannot say this is the center of the network. There is no center of the network. It's a big cloud and there is no single control point. So voluntary adoption of technology is a very important part of how this internet works. Innovation is done bottom up. It's also one of these properties that we've seen a lot. People basically say, we want to get something done, they get together and they make it work. Bottom up collaboration. Collaboration where needed, by the way, and competition where possible. Because there's a lot of competition in networking. But in order to make things work, you need to collaborate at some fronts. And that's where internet governance comes into play. And that collaboration is usually between parties that have an interest in making things work. The stakeholders that are involved in making things work at the level where you do make the things work. If you want to talk about the internet in Kyrgyzstan, you have to talk about the internet in Kyrgyzstan and not in the US. You have to get the people together to do the work. That's what's happening here today. If you look at the global scale, there's also some collaboration needed. That collaboration is depicted here in the internet ecosystem sphere, and I'm not going to go into the details of this, but the collaboration where needed is in standardization. It is in the places where we have the names and addresses, because addresses are globally used, so we need a global system of distribution. This is where the regional internet registries play a role. RIPE-NCC for this region. For naming, we need the DNS. That's a highly distributed system, but it has a hierarchy, and a hierarchy has a central point. That's the root zone, and the root zone is managed by ICANN in the US. But it's managed through a system of collaboration, a multi-stakeholder process which drives policies. At local, national, regional, and global level, you need some policy developments. The minister just talked about that. Education is needed, capacity building, and of course we have the users in this whole ecosystem. Those are all the pieces. So, what I would like you to take away from this picture, of this hourglass picture, which we talk about in Internet architecture a lot. What is the hourglass and how does it change? Because this is a very simple model, of course. But what I want to have you take away is that you have different players at different layers. You have different people who manage networks. You have different people who build applications. And there is collaboration and there is interaction. And innovation at the bottom will drive innovation at the top. When I started doing internet, I had a dial-in modem, 36K of bandwidth. I couldn't do video at the time. I could download some files, but I couldn't do video. I could do email. I could do web pages, but not with gigantic images. That took a lot of time to load. But now, because of applications in the top creating value, people have invested in the networks. Because the networks grew and grew in capacity, we have applications like video streaming on the top. And this is a cycle that will continue. Applications, innovations at both layers is done by different players. Once you start coupling these things, once you create verticals, the innovation speed at both sides is coupled. And that might not be a good thing. That might change the nature of how the internet develops. Horizontals, different players, different things. So, new topic. I talked about collaboration. One of the things in which we collaborate is in the creation of open standards. I have a bit of a history in the internet, Internet Engineering Task Force, which is the standards organization, in which standards like TCP/IP and all kinds of other standards are developed for global use. And I want to talk a little bit about that, the IETF. Because every time you use a device on the internet or you use a service on the internet, there's a whole protocol soup that you use, a whole set of standards. If you go on the internet using your phone, for instance, in this environment, you will use the Wi-Fi environment. And this is in the network layer. So is in the bottom side of the hourglass. That's an 802.11 standards is developed by a standards organization called the IEEE. You will do a lookup that's done by the IETF. There might be a network address translation box in the network here in the hotel. There's no standards for that. That's proprietary. Style sheets done by the W3C, which is the style sheets say CSS say how your web page is going to look. That's a standards done by W3C, which is the standards organization for the web. The internet and the web are two different things. The web is an application that runs on the internet. So a whole bunch of protocol soup on the higher part of the hourglass, the lower part of the hourglass, but also in the middle of that hourglass. TCP/IP I already mentioned, it's the IP protocol, and TCP has its 40th birthday. BGP is the routing protocol. That's what makes these nodes in the network talk together. It's a bunch of standards that we use. What we've realized not so long ago is that the way that we've been creating standards on the internet share some common properties. And we, that is the ISOC in collaboration with the W3C, IEEE, IETF, have created a website called OpenStand in which we publish the paradigm that is at the basis of this standards development. And there is a few keywords. Sorry, this was a Dutch word that I literally took. There are a few keywords that play an important role. And we believe that this way of standards making is a driver for innovation and borderless commerce. These, and you don't have to read the slide will be online, but the keywords are cooperation. That's something I already talked about. Collaboration is one of these things by which the internet works. Adherence of principles. Well, of course, if you do standards development, you need to adhere to certain transparency principles, to making sure that your consensus process is well defined, that you actually have a process so that everybody who participates knows what the rules are in advance, that there is a balance in the needs of participants, that things are balanced off, and what we think is very important, there's openness in the process. Everybody is able to participate, and all the decisions are made in a way so that informed parties can join the club. Collective empowerment. Make sure that standards are based on technical merit. That's a very important principle. The technical merit is what matters. Provides global interoperability, scalability, stability, and resilience. If you want to build something for the internet, all these things are very important. The availability and the voluntary adoption. That last thing is very important. Any standard made for the internet is based for voluntary, is assumed to be made for voluntary adoption. That means if a standard doesn't serve the market needs, it will not be adopted by the market. It's just, there's no central mandate that says you have to adopt something. It's all about collaboration. And if we talk, for instance, about IPv6, there is no central place where people say, we mandate IPv6 to be introduced in the networks tomorrow. This is a voluntary effort of all the people in the internet. And by the way, it's working. People are going to IPv6 because it's important. People understand this. So the IETF is one of these standards organizations. The IETF, the Internet Engineering Task Force, is a loosely self-organized group of people who contribute to the engineering and evolution of the internet technologies. It is the principal body engaged in the development of new internet standard specification. I'm reading this out because this is the mission statement. This is the mission statement of the IETF, and it's published in a document called RFC 4677. RFCs are the publication series that the IETF uses to publish its standards. The name Request for Comments comes from the very early stages where there were pragmatic reasons to call those specifications requests for comments, because there was all kinds of politics involved with calling it a standard or a specification. The mission of the IETF is to make the internet work better. That's the thing that they try to do over there. By producing high quality, relevant technical documents that influence the way that people design, use and manage the internet. Now the IETF is, you might have heard of it, but it's a voluntary organization. People can just go there and join and do the work. And by joining, I mean join a mailing list. The work is formally done over the internet on mailing lists. You don't have to go to meetings. You can subscribe to a mailing list, read the documentation, and if you have meritful input to the process, if you look at the technology and think, this is not right, or this can be done better, then you can participate and your comments will be taken into account. The fact that it's a voluntary organization doesn't mean it's not organized. We have a management layer called the IESG, the Internet Engineering Steering Group, which has under it a number of areas, each with their own working groups. Each working group has a chair. The areas have directors. The directors together form a management board called the IESG. There is an oversight body called the Internet Architecture Board, the IAB, 12 volunteers. I've been so lucky that I have been able to chair that group. And then there is a bunch of other organizations that have their own acronyms. There's the Internet Research Task Force, where researchy work is taking place, also on mailing lists and also organized. There is a secretariat that maintains the website, that scouts for the meetings and figures out meeting locations. And all this is organized under, because it's, you know, a bunch of volunteers, they need a bank account. That's what ISOC does for them. The areas are organized among, you know, technical areas. I'm not going to go into detail, that's probably a little bit boring. But we've got a number of them. So I'm looking at Frederik to say, oh, I've got two more minutes. IPv6. Shall I just tell you a little bit about IPv6, because that's the thing that is one of the internet technologies that is actually very important for sustained growth of the internet. And the sustained growth you can see from this picture. This is a picture that one of the IETF hosts, somebody who, you know, pays for some of the meeting at some point, introduced. This is a slide from Ericsson. And what you see in this slide is a sort of evolution of the internet. When the internet started, it was an internet of places. It was computer institutions at universities or research centers that were joined, mainframes. If you had a place with a computer, you wanted to join it to another place with a computer so you could share resources and information. That became, you know, that went from institutions to homes, but there still was only one connection in the home when I started to join the internet over a modem. That was the internet of places. What happened in 2000, I would say, between 1990 and 2000, is that the internet became of people. We have these smartphones. We walk around with our own internet connectivity thing. In our house, we have, the kids also have a computer. So in our house, there's already a number of devices and a number of people that use the internet. So the internet became the internet of people, and there already you see a problem. The internet protocol, IPv4, was designed with 4 billion addresses in mind. 4 billion addresses. Do the math. We've got more than 6 billion people on this planet. An internet of places might have worked with 4 billion addresses. An internet of people doesn't. Not with 6 billion people. And now we're moving to an internet of things. Predictions are that we will have 50 billion connected things by 2020 globally. 50 billion. 4 billion addresses don't cut it. It's not enough. That's why we collectively, and this is collaboration, there's no central mandate. This is why we collectively have to work for IPv6. Market predictions are that there's $1.2 trillion of value in that Internet of Things. So there's a market there. IPv6 deployment. There's not really a lot, but it's becoming significant. You see this growth curve. We're at the Internet Society, we measure this stuff, or we collect measurements from others, I should say. This is from Google. This is traffic that Google sees coming in over the internet. And what they measure is the amount of traffic they get over V6, over IPv6, and the amount of traffic they get over the legacy protocol, IPv4. And they see that we just reached 5% this month. 5% of the internet traffic is over IPv6. And currently that growth curve is faster than the IPv4 growth curve. That's important. It's not a lot, but it's important. And what we've seen is that when people turn on IPv6 in their networks, there will be significant traffic on the networks. There are networks that see 20 to 30% of their traffic internally over IPv6. This stuff is real, there's no denying. And I'm going to close off with this statistic because I wanted to give a Kyrgyzstan type of note here. Unfortunately, Kyrgyzstan is not very high in this statistic. It's not very green. There is some IPv6 out there according to this measurement, and I don't know the details. There are people in this room that probably know this situation much better than I do, I think. Users, 0%. There are no users, end users in Kyrgyzstan that have IPv6. But there is some activity. The networks seem to be enabled according to these statistics, and I think that is fairly good news. Because if the networks are enabled, then the switching costs are lower than if you have to start from scratch. And with that, I'm going to hand it over to Frederick, and thank you for your attention.